It is great to have as colloquial speaker today Rana Adikhari from Caltech. Rana was a student, an undergraduate student at Florida State School, where he grew up. I was then a graduate student at MIT, and I guess Ray Wise was his advisor. And then it's now a number of years, he's been at Caltech, where he has a program that is, that starts from the point of view of quantum measurements and LIGO, but is broader than that. Rana has received a number of awards, mainly related to LIGO activity, but not only. And so, without further ado, Rana, the floor is yours. Also, Rana, sorry, I forgot this. Rana was instrumental in bringing LIGO to India, or at least having LIGO India started, which is something I'm told just had groundbreaking. So hopefully soon there's going to be a fourth interferometer if you count Virgo more.
Yeah, counting is a difficult part of mathematics and science.
Yeah.
What counts as one? I feel like I'm echoing here, like there's multiple sensors and actuators.
That's a close microphone. Always.
I think you did this on purpose to underscore my point about control systems. So. A good demonstration.
I think it's a matter of having try now.
All right. People can hear me? Yeah. Very good.
All right. Just adjusting the volume. Huh?
I'll tell you about a number of things, but I'm not going to tell you that much about the LIGO experiment. I think people know about it and how it works. It is a Michelson interferometer and it measures things. That's kind of how it works. The last time I came here, it was 2016. It was in February. I think Bob had invited me. And there were more people in attendance that day for some reason. I felt like maybe you all think I haven't discovered anything as interesting as that one thing back then. Maybe that's the reason, but let's see how it goes at the end. When I came here that time, at the bottom of my thing about how many detections, it said approximately 1.5. I think I had to twiddle 1.5 because we weren't sure if there was more than one. It seemed like there was a hint of 2. And 2.5 was if you're a real optimist. But I think 1 we were pretty confident about. And now we're at this level. And let me just tell you about this plot. So on the y-axis here is mass and solar masses. And what do these little graphics mean? Let's say this little one means that there was something with 7 solar masses and another one with 12, and it merged into turning something that was about 17 or 18. And that's what all these things mean. And the x-axis this is a bad plot. The x-axis is chronological for the black holes. These are all the LIGO, Virgo discovered black holes here. And it's not chronological for the electromagnetic ones. Why would I mix up axes like that? I don't know. But this is a partly AI generated talk. So that's, blame it on that. Now I did this because these are not really mine, but I wanted to show you that the electromagnetic ones are mostly little ones. And then these red ones are the inferred black holes from observations like radio and X-ray and so on. But the real surprise, if you look at this, by the way, this is the QR code about the latest release. This is, I forgot which one this is called, but it's our latest gravitational wave catalog. And so all the new ones are listed in there, and they're all from this end. But you can see the real surprises are these monsters down at the bottom. And who would have thought 10 years ago when I came here? I think 10 years ago when I came here, I said to you, I didn't tell you the truth back then. I came here and I said, what a surprise, we had never predicted this. And 2 black holes, which were each about 30 solar masses, had smashed together and produced a thing that was about 60 solar masses. And 3 solar masses were converted into energy. And isn't that fantastic? But what I didn't tell you is a month before the detection, I can now say this, a month before the detection in September of 2015, I was on a YouTube video and someone asked me, what do you think is going to happen in a month? And everyone else was pessimistic. And I said, we're going to find lots of stuff. And the first one that we find will be roughly 30 solar masses apiece. And that's on YouTube and you can find it. So I was correct a month before the detection. Just couldn't tell you at the time. Anyway, these are way bigger. And I really didn't expect these ones. I can just say that for sure. And I'm not going to come back and say anything different again. But the fact that there's black holes over 100 solar masses, I took astrophysics classes and things like this, and there was never any story about how you'd make anything this big, except when I was a grad student at MIT, Hans Bethe came. I don't know, if you're younger, that sounds like I'm talking about like Isaac Newton came to my school or something. But Hans Bethe was over 90 and still cooking. Back then, this was in the late 90s. And he came and gave a colloquium, and he had a deep, raspy voice, which I'm not going to try to imitate. But he said, LIGO is not going to find binary neutron stars that much, but you're going to find binary black holes. And the reason is that you have globular clusters in galaxies. And in those globular clusters, there's enough tidal gravitational friction that the binaries will inspiral faster than you expect. And so you get a lot of heavy things. And I think that's turned out to be the truth. So good for Hans Bethe so far. But I kind of want to tell you, a lot of people, I think when I go around and have conversations these days, it's about what are you doing with your AI agents in the middle of the night? And that's kind of the vibe of the talk I'm going to give you is what kind of things that we can do now that I think I would have thought I need at least 15 grad students to do or 10 years. And I think they're a lot faster now. And maybe it's not the kind of things you've heard about for AI before. I'm not talking about signal processing or analysis or bag decision trees or those kinds of things. It's more about how do you tune up your experiment in the right way. And I think we have to do it. And a lot of experiments that are now going on, maybe outside of CERN, maybe at the small scale, are a lot about precision measurement. And a lot of it is actually stuff that's going on here. I think, well, I don't have to tell you about the history of Stanford physics, but just within LIGO and then also within atom interferometers and then searches for axions, things are really at the precision frontier. And we're doing it partly for applied physics reasons, but I think also for the search for new fundamental physics. There's the high energy direction, and there's the low energy direction, and I prefer to go low, and others go high. That's my Obama jokes. So, what are the recipe ingredients? The usual thing you hear about is quantum measurement, and I will tell you about that at the end. But the main point I want to make is more about optimization and optimal control. But I think those are areas that they're not typically you wouldn't hear about in a physics talk, but I think at least for gravitational wave detectors and now tabletop experiments that I have in mind for quantum gravity, we're going to need to do really optimization of the full experiment and new controls beyond what you'd expect with normal TID filters and so on. So this is where we are in the LIGO world today. And these are the three operating detectors in the world. And on the x-axis is frequency. And most of our black hole mergers are sort of in this low frequency audio band, sort of this. And the neutron stars will merge out here, higher frequency band. But it's all basically audio world. And these are the two LIGO detectors. And the green one is the third one in the world, Virgo. And it's getting pretty close. It's within a factor of few in this band, but in most of the frequency band, it's off by factors of several. And it's only 30% in length. So it's more to do with the experimental design rather than the length of the detector. And but there's a few limits, so I want to tell you about those. So there's the fundamental quantum limit, and at the high frequencies, this comes from just the usual shot noise, that's just the counting error. But at the low frequencies, this curve has to do with the quantum back action. So it's really the radiation pressure of the photons buffeting the mirrors and shaking them around. And it has a kind of funny shape, which I'll explain to you at the end, but I want to give you the enjoyment of trying to figure it out while I'm talking. You'll notice it's not exactly like 1 over f squared. You may wonder where that comes from. Anyway, but the fact that this shot noise is so low, I would say, has to do with the fact that we have incredible lasers. So thanks, Bob, for all the nice photons. And then we have, an incredibly low vibration background. You can look at these numbers here. The strain is 10 to the minus 23 tensehertz. And that's, a motion of 10 to the minus 19 to the minus 20 meters, which is an unbelievably small number to have for macroscopic objects. And we really have it. It's really a lot due to the work that has happened at Stanford over the years, both in the seismic pre-isolation led by Brian Lance here, and then I would say also in the mirror system by Mark Rollins. And then this orange curve down at the bottom is just the thermodynamic fluctuations of the mirror surface. And that really has to do with the fact that we haven't tamed the issue of two-level systems in thin films. I mean, we've made as much progress as we have, again, due to Stanford's work in two-level systems and understanding glasses, but there's, I think, at least another order of magnitude to go. So there's yet more hope. Yeah, as I say here, this is just not enough photons to get shot noise lower. However, more photons, more problems, I say. I think when we first got started, we were in the world of saying, let's get more and more light into the system, and the more laser power you have, if you double the power, your signal goes up by a factor of 2 also, so that's great. But then you start running into the real thermodynamic limits. And the first one is just classical radiation pressure. I noticed maybe 20 years ago or something, when we turned on the lasers, that the mirrors would always point in the wrong direction. And then I would go in there and turn it back in the right direction, and it went on for a few weeks. And then finally, I don't know who it was, somebody sitting next to me said, 2 times P divided by C is equal to force, according to dimensional analysis. And then we worked out the equation of a mass on a spring and realized, oh, it was the radiation pressure that's always misaligning all of our optics. What are we going to do about it? So we invented the idea of feedback, not for the first time. And it turned out that that was good enough for probably a decade or so. And then we started running into another kind of feedback instability. And those of you who have ever gone to karaoke bars maybe understands this next one. This is the idea of parametric instability, whereas the volume's too high, like we just heard here, and the microphone's too close to your mouth, there's a kind of unstable whine that happens. And that happens in our LIGO interferometers also. The laser power is so strong that the acoustic modes of the mirror travel around the full 8-kilometer system and come back. And some of those acoustic modes have a positive feedback and some of them have negative feedback. So if you look at the acoustic spectrum of all the modes ringing, some of them get suppressed as you turn up the laser power and some of them go up. And the ones that go up, they just go out of control. And so there's 40-kilogram pieces of glass that are ringing at 50 kilohertz, 80 kilohertz, or something like really ultrasonic. And for some reason, they have positive feedback and they ring up. And so it's like that old story you might have read with the little boy in the dam. The little boy's putting his fingers in the holes to keep the water from going out. That's how it feels like. We turn on the system, and every time we increase the power by 5% or something, and other things start shaking, and we have to try to dampen it. And it's kind of a nightmare because they drift all over the place. It's just really hard to control. I mean, we still appreciate the laser, but still, it's a problem. Maybe the toughest problem that we face is thermal distortion. And we're now at the level where there's about 0.5 megawatt in each of the fabric cavities, and the beam is about this big. And the first thing that happens is the surface gets distorted, but then the absorption is not uniform. So you end up with a crummy pattern. Nice. It's non-spherical, it's hard to treat. And then finally, the coatings themselves have little flakes of metal stuck into it that we don't want. But if you have optics, your optics have metal flakes in them. I don't know what to tell you, but if you didn't know about it, sorry to be the bearer of bad news, but that's how they are. And those things get hot, and usually they explode. And so once you've been running your system for a while, if you examine the optic with a microscope, you'll see little volcanoes on the front, and they're horrifying. If you love your optics, don't look at them too closely. I'm sad about it. And then, of course, quantum back action, as I mentioned. So we're also at the level where now most of the noise below 50 hertz or something is just this rumble of radiation pressure. And we need to get rid of that too. So I thought, I don't really know what to do about thermodynamics because that's hard. And I also don't know what to do about quantum mechanics because that's just the way it is. What am I going to do about that? However, I showed you this brown thing here, which is the gap between quantum mechanics and where we are. And it's something like an order of magnitude. And that's addressable even if you can't circumvent quantum mechanics. So I got together with the smart folks at Google DeepMind a few years ago. And during the pandemic, we all had time in our hands and we all passed the time with strange hobbies. I mean, you don't have to talk about it now, but we all did things. And this is what I did during the pandemic. We ran a lot of simulations and tried to figure out what could we do to remove this stuff that was in our control band. And what is this stuff? It's kind of here in this graphic that Google has generated. But that first thing that I showed you about angular radiation pressure torques. So the mirrors are like this, and when they go like this, the radiation pressure kind of stiffens that mode. The mirror it makes it hard for the system to rotate like this. And that mode goes unstable because it takes the light some time to travel up and down the 4 kilometers. And that feedback stability happens to have the wrong side. So to keep the system running stably, it's a feedback controls challenge. And I don't know for how many decades I've been traveling to the LIGO sites and adjusting little knobs by hand, and the controls engineers would laugh at us. Oh, why are you adjusting little numbers in your PID loops? And by the end of it, we have something like a 20th order set of poles and zeros that we're using for feedback, and it's still just not enough. We're at the limits of what we can do. We have to control the system against ocean tides and radiation pressure, and we have to not touch the mirror at all, the level of 10 to the minus 19 mirrors. And it's just tough to do. So what do? We made a simulation of the system and thousands of simulations. And then Google probably melted some ice caps by training their reinforcement learning algorithms on this. But we tried all kinds of things. And we did a lot of, for the ML people, we did a lot of domain randomization and various learning strategies. But in the end, the network that we needed to solve this wasn't that involved. But I'll tell you a couple of keys in how you do it. So, here's what you want to do. You want a controller that controls your environment that well. In our case, that's LIGO. So we made a simulation of the LIGO system based on measurements that I took and fed it into the algorithm. What does the algorithm do? It looks at the low frequencies and says, have I been controlling this enough? And then it looks in the band where you're looking for gravitational waves and says, have I been quiet enough? And it multiplies those two things together and then uses that in a feedback loop to change that controller. And it's kind of like a gradient descent at that point. But the number of degrees of freedom are huge. So if you're a controls engineer, you know that there's methods like H infinity and linear quadratic regulators you can use. And those might have 50 terms in it or so. This thing in the end had something like 500,000 variables. And how do you do gradient descent on 500,000 variables? I think if you haven't been into doing a lot of neural network stuff, I'll just tell you that for the physicist, what it means. It means that when you're doing optimization, you just don't go for the optimum. You go for the good enough instead of the optimum. Because in a space of 500,000, I mean, who knows? You can't really do global optimization. But the beauty of this technique is that when you use this multiplicative cost function instead of additive cost function, you're able to really regularize the reward space and get to a good enough answer pretty quickly. Pretty quickly, I think this takes about 24 hours to train on a modern, like an H100 or H200 GPU. So not that bad. So what's the issue? This was our background floor. We did these frequency domain rewards. And at the end of it, we were able to do, I was aiming for a factor of 2 or 3. That's usually a big success in science. But we got this factor of 30 beyond what we could do with linear feedback systems. And I wanted to put the secret up here, but I don't feel like we should have any secret sauce. I think the secret was not in the machine learning at the end of the day, but it was in really, really understanding what the experiment's doing. And for that, there's textbooks about system identification, but you need either a person, I mean, in this case, it was me, but in the future, you need an autonomous AI agent who will do this stuff. And the way we did it mathematically is to say, there is a Fisher matrix which describes all the uncertainty and all the parameters you have, or the covariance matrix of your system. And that has to include not just the static behavior, but also the time variation. And the time variation is the key. If you're a controls engineer, you know that if you have a linear system with Gaussian noise sources, you don't need any of this fancy stuff. You can just have a fancy PID loop and it should work for you. But we live in the real world, and the real world's non-Gaussian. And so the optimal feedback system for non-Gaussian systems is a nonlinear controller. This algorithm gives you the optimum nonlinear controller, or the good enough optimum nonlinear controller. And why does it matter for you? I'd say if you want to do precision measurements, you're often doing some sort of feedback where you want to keep the feedback out of your science band. And the level to which you can do this, we've always thought it was limited by some sort of linear systems analysis. And there's this usual thing called the waterbed effect. People say, the more gain you have at your control band, the more you're going to inject noise at the higher frequencies. There's sort of this, there's nothing you can do. It's the Bode sensitivity integral. It just has been around since forever. With nonlinear systems, that is no longer true. And so this is what we were able to get. This is, again, the LIGO noise, this purple one that I showed you before. The green dash curve is 10 times below the quantum radiation threshold background that we're trying to get beyond. And the blue curve is what we were able to get with DeepMind's reinforcement learning. And I just want to point out, not only is it well below the back action limit above 10 hertz, but it's well below what we can achieve even below there. And so why does this matter to you? It has to do with the frequency mass relationship of black holes. So if you have a black hole of 1 solar mass and you flicked it like this, it would ring at about 12 kilohertz. That's the tone. And the tone goes like 1 over the mass. So if you have 100 solar masses, like typical sources we have, that's showing up at about 120 hertz. That's a little bit deeper than my voice. But the real ones that we want to go for are more like 1,000 solar masses. And if you're in astrophysics, you might say, ha, those things don't exist. And I would say, yeah, but that's what you told me a decade ago and you were wrong. So maybe they do exist. But if they do exist, we're going to need some sort of better experiment to find them. So this is one of the ways. We can do this now on a few of the feedback loops, and it seems to be stable for hours. So the idea of having neural networks run the LIGO interferometers is not as far-fetched as I used to think. So how to do it? This is my AI segue, I would say. It used to be, if you want to do any of these things, you would have a team of people go off and build a great simulation environment for years and years, and that's what we used to do. But just this year, in my group, we've basically rewritten all of the LIGO modeling software, and that includes frequency-dependent quantum optomechanics, thin films design, detailed optical modeling software, and the full FEM package, which solves many, many of the LIGO problems. And it's not, I'm not a great programmer or a software engineer, but now you have these agents like Claude Code and Codex and things like that. And I know, I can just, from wandering around today, I know like a lot of us are up awake after midnight playing around with our AI agents and have deep conversations. But personally, right now, like my laptop is solving 10 different problems. And a year ago, if you had told me that, I would say, what a waste of time, because it's like garbage in, garbage out. But this year, anyway, it seems to be less garbage out for the amount of garbage in. And it's been very valuable because now we're able to make extremely detailed models of what's going on, and it's very low friction to create these models. And for things like doing optimization of controls, you really need to have the model accurate to the percent level in order to get the best out of your controls. So I'll tell you a little bit about quantum sensing and where I think we're going. I was yeah.
Sorry, can I ask a question? So you said that it's an optimization problem of 500,000 parameters. So can you help me understand where does these parameters go to? I assume you have a handful of error signals and a handful of knobs you can control, and then each error signal gets convolved with a function with the parameter. That's how it end up to be that large.
Yeah, that's right. So for instance, if you have a neural network that has let's say a few layers that are tens of maybe let's say 100 input samples or something for that. Each one of them may have 10 or 20,000 input parameters. And so it's just the size of the network that you use. And I'm glad you asked that question. So for 2 years, I didn't make any progress on this by myself. And that's because as a physicist, I said, I totally understand the physics of my problem, and there's no way I need 100,000 parameters. I need like 100 parameters max, maybe 200 if I'm feeling excited. And the computers were like that. I was first doing this stuff on P100s, which are now, like, it's even blown away by my laptop. And that's about the kind of model you can handle. And I didn't have the patience to train something for 96 hours because I didn't think, if it's not optimizing after 96 hours, it's time to try something else. It turned out to be wrong. So when we started working with DeepMind, what they showed us is that as you make the network deeper and deeper, it's operating in a much higher dimensional space. So just like in 3 dimensions, we have a hard time getting through that wall. And in 4 dimensions, you just step around the wall, right? And in the higher dimensional space, that seems to be what's going on. When we see blockages with small networks, we're able to increase the deepness of the network and get around it and find a better global optimum. So I don't know if there's anything fundamental about that, but that was our experience. So on the optimization side is sort of where I'm going with quantum measurement. I wasn't a believer in squeeze light that much. I mean, I understood sort of the physics of it, but I had never seen anything useful out of it besides PRL. There's nothing wrong with PRL, but that's all I used to see out of it. And in GO600, which was the German gravitational wave detector, they started demonstrating an advantage at high frequencies by using squeeze light. And then at LIGO, we got onto the bandwagon and we started also doing it. And we found you could squeeze the light in the phase direction and increase the noise at low frequencies for amplitude fluctuations. And we were okay with that. We got about a square root of 2 advantage in phase sensing, which is directly a square root of 2 in terms of distance into the universe. So that was a good win. And then the group at MIT, along with Lee McCullough from Caltech, then pioneered this idea of frequency-dependent squeezing, or I thought they had, but it turned out that was also an older paper from 2001 from Jeff Kimball and Kip Thorne and Sergey Vichan and others. And then I realized that was actually an even older idea from Bill Unruh from the 1980s, the Unruh-Hawking radiation. But it was finally implemented. So 1983 to 2001 was the time it took to make an experimental design. And then 2001 to 2023 was the time that it took to implement it in the detectors. But now we have a system, and that's the red curve I showed, which has the funny low frequency part. That filter cavity allows us to do phase shifting on the squeeze light. So we squeeze the light, we bounce it off a cavity, which acts basically as a high pass filter. And so below the corner frequency of the cavity, it gives us a 90-degree phase shift. So that means that ellipse shifts by 90 degrees, and you're squeezing the amplitude fluctuations at low frequency, and you're squeezing the phase fluctuations at high frequencies. So you're able to get the best of both worlds, the regime that you want. But it's still Gaussian. The probability distribution that you see when you measure any of these variables is still Gaussian in any of the quadratures. And the frontier is going beyond Gaussian. So there's a lot of well-researched limits about what you can do with Gaussian states and linear systems and its optimality under certain kinds of loss. And there's nothing you can do about it except go non-Gaussian. And why so? So in 2001, Daniel Gottesman, Alexei Kitaev, and John Preskill of GKP came up with this idea of doing grid states, that instead of having all of your uncertain, this works better with this diagram. So here, this is sort of the delta X delta P Heisenberg uncertainty principle. And it says that the product of delta X and delta P will be greater than or equal to H bar over 2. And it's satisfied by this. And now if you take that sphere and you squeeze it like this, the area is still the same. So delta X, delta P still satisfies the same criteria. So that's fine. But then you might ask, what's that thing? Is that an AI hallucination in your slides? Or is it really something in physics? Well, as it turns out, the Heisenberg uncertainty principle is the only thing you have to obey, but you don't have to obey the idea that it's all in one blob. So you can have your blob separated out across the space. And as long as you're still respecting the total uncertainty, there's nothing about what shape you need to have. You could distort this ellipse into a smiley face if you want to, and if that state works for you, then it's still legal. So what these three discovered back in, I think, 2001 is that if you made a grid of states, each one having h bar over 2 divided by n, or grid states that you have, you can use those to do almost sub-Heisenberg sensing if you do some sort of post-selection of the signal. So if you imagine again, you have a grid of those little balls, but now those little balls are much smaller. You can say, if the grid spacing is big enough and I make a measurement and it's not close to 0, I can reject it. Because as an experimenter, I know that my mirror didn't move by a meter or something in the last nanosecond. So I can exclude numbers which are too large. So you can do a little bit of this post-hoc selection and do better. Another way you can do is observe what we call a quantum non-demolition observable. So you have this delta X, delta P commutation relationship, and that leads to this uncertainty, and that leads to quantum back action. But you can also make observations which are muting with itself at later times. So if you measure the energy of your oscillator, let's say, you can do so without the back action penalty. And so one idea we have, and Lee McCullough is following this, is that you can run your interferometer exactly on the Michelson dark fringe. So to first order, you don't get any signal. You're really at the bottom of power versus length. And the idea there is if you have enough energy in the gravitational wave, it'll scatter a photon out of that mode and it'll actually come out of your dark point. So you can count photons and measure the energy in your signals. And that's a way to get beyond some of these limits. And then finally, another way is to actually make customized states. And customized states is the way we actually would go. Here's some examples. So this is sort of my cartoon version of one of the papers from Xanadu. And they showed this kind of thing that if you overlay multiple squeezers, you can get different quantum optical states. I don't know words. Ooh. Exciting. So I'm just showing you here some sliders, and as you change the phase and amplitude of 2 squeezed light devices here, with some sort of heralding, you can get more complicated states on the output. This doesn't look like any kind of usual vacuum state or coherent state. It just looks like a non-Gaussian state. And it's definitely non-classical because it has negative going regions in this Wigner probability distribution plot. So it's just a simple example of what you can do. And there's many other ways of making non-Gaussian optical states. And nothing is for free. You can do this, but then there's still a question of how do you get all the information out? So people have studied this before, and they've shown if you use non-Gaussian states, the total quantum Fisher information you can extract from your linear system beats what you can get with Gaussian states under certain assumptions. But it still remains, how do you actually get that information out? It's fine to have a lot of quantum Fisher information, quantum information, but in the end, we're classical people, so we have to project it into some sort of classical observable for us. And this is not one of those problems that it's easy to solve by gradient descent. I wouldn't say it's really an NP problem, but it's kind of like doing an inverse design. So once you have the experimental layout, it's easy to run the forward calculation and figure out what to do, but it's difficult to do the inverse one. And so this is some work with my collaborator, Mario Cran, and my former postdoc, Jonathan Drury. And what we said is, maybe it's time that we can do better. And they said, how did you actually design LIGO the first time around? And I said, I was a postdoc, and I was given this job to optimize some numbers. And I had this software called MATLAB. And MATLAB had a thing called fmin search, which did gradient descent. So I just ran that 1,000 times. And then that's what we built in the end, is whatever MATLAB told us to build. And in retrospect, probably not the best optimization. Maybe we could have done better. So this was our idea of doing better. We said, let's imagine you don't have any budget constraints and you could just use up all the land in America to build your gravitational wave detector. What would it look like? So we built this whole thing. And I said, let's just try out to see which one's best. But it had 10 to the 8 possibilities. It was kind of impossible for us to calculate in a human lifetime. And what Mario's group excels at is doing these huge dimensional, real global optimizations and figures out how to turn a discrete programming problem into a continuous problem. Using this, he was able to find several designs that beat the current LIGO design, and it's really just by adding a few components to doing optimization. So I thought that's fantastic. What should we do next? So we started working on this idea of making neural network surrogates. So every place in our simulation where we run into an expensive simulation that requires quantum computing or huge GPU clusters. We ran tens of simulations, approximated it with neural surrogates, and were able to get speed ups of sort of factors of 10 to 100. So, what's it all good for? Well, LIGO is already built and running in the US. But as Giorgio has mentioned, there's a new one coming on board. And that's the one in India. So I've been traveling there, I think since 1975. But in 1975, I wasn't an effective science communicator. And so I wasn't able to do what I can do now. But since 2008, I've been traveling there, trying to encourage the country of India to get a gravitational wave detector going. And it started from just laughter and complete disbelief to, well, maybe, how hard can it be after all? And there's sort of waves of excitement and despondency over the years as it's coming and going. And now that I say it, 2008 sounds like a long time. Well, a decade ago, 2008 wasn't that long. So there you go. But now it's been almost 20 years to go. But I thought it was a fantastic thing to do because it's so far away from where we are in the US. And there's a lot of people there who are interested in science. But when you want to do a multi-detector observatory across the world, what are you going to do? You want to do triangulation. So you want the detectors to be as far apart as you can to get a long baseline. And so we thought about Australia and we thought about Russia and Canada and all these other places. But this seemed to be the only one where I had any kind of special influence. So I thought, this is the place for me. And here's what happened. So anyway, I guess this is being recorded. I was going to say, don't record this, but this is just my personal view of what went on. We started talking about it in the I would say late 2000s. We built a consortium, and it was led by the people who were most excited by it at the time. In 2016, after I visited here, I moved to DC, and the Prime Minister of India also showed up in DC, allegedly not to meet with me, but allegedly to meet with Obama. But come on, me, Obama, what do you think? So we had a discussion very briefly where he said, what do you have to say for yourself? And then I gave an impassioned speech about space and cosmology and science and the youth and the future and all these things. And he nodded, and I'm not sure if he got my whole message, but anyway, we signed some documents, I would say. And so we had the goodwill of the government, and we started working, but we didn't really get funded. We picked a site in the middle of nowhere, and it's very hot there. But it was a place where we could get land. And then finally in 2023, that's been about 3 years ago, we finally got the full funding, about $300 million from the Indian government. Along the way, we've kept in storage another, we have a LIGO in Louisiana, we have LIGO Washington, and then the third one was what we call LIGO Warehouse, where there's a bunch of boxes that has another LIGO inside of it doing nothing. All these, well, not doing nothing. People use it for spare parts, what I understand. But LIGO Warehouse is about to be shipped to the dock in Seattle and shipped to India. And groundbreaking happened just a couple months ago. And bulldozers are on the ground is being leveled. And so we're on track to have a third one on in a few years. And that's kind of what all this stuff is about, is, we're building this complicated simulation software, AI-controlled interferometers and AI-optimized designs, and non-Gaussian optical sensing. So our plan is to roll all of that into the new one so that this third one will land a little bit above where the existing ones are. And this is a little toy model I wanted to show you about why do we need these things. So this particles here is the effect of a gravitational wave. We're sort of looking down on a ring of particles in space as the wave comes down. And I'll speed up the thing to make it more exciting. And so let's see if I can get it. Okay, so now it's a linearly polarized system. It's just stretching and squeezing like this, and the rotations are happening. And so now you can see, depending on where in the sky it comes from, you can get smaller or bigger signals. Just have trouble doing this one. Well, this is the opposite of what I wanted to show you. But here, the signals are very prominent, and the two US detectors not really there in India. And you can see if now you make a sort of circular polarization, you get more of the signal in the other interferometers. And that's sort of the point of this. All along, we've been operating with two LIGO detectors, which are both in the US. Here's the globe. And they're L-shaped. And in the 90s, people thought, hang on, maybe this field is kind of sketchy. What if we only get one signal once in a while? We won't know if it's real. So they co-align the detectors as much as you can on a globe. But when the signal comes into the US detectors, we see one polarization of gravitational waves. And the other polarization carries a lot of information. So I don't have an animation for this. I'll just do it for you here in the live audience. You can imagine some disco music playing while I'm doing this. So if the two black holes are inspiraling like this, as the hole comes closer to you and further away from you, feel stretching and squeezing in this direction, but nothing in the transverse direction. However, if it's face on, and face on here, something like this, if the two things are going like this, then you feel a different gravitational strain than if it's like this. This is usually the most entertaining part of the talk. Anyway, you can see maybe why, just from Newtonian gravity intuition, why you get a different stretching and squeezing factor. And it matters a lot to us. So if you want to figure out from one of these waveforms what's going on in outer space, you really have to know what's the inclination of the binary. And it's not just for basic, well, we just want to know things about astronomy, but the purpose of these black holes, yeah, sure, it's to understand black holes and it's to understand the population statistics or so on, but I'm not an astronomer, I'm a physicist, and I care more about what's going on in the universe and how many black holes we have. And for me, the black holes are actually a backlight to the universe. They're happening, and as it turned out, as Hans Bethe said, there's way more of these than we thought, and they're really illuminating the universe from behind. So what we now see is what happens when the universe is uniformly illuminated by gravity. And that's really what I want to puzzle out. And if you've ever, gotten into your car with polarized sunglasses on, you can see from the windshield that there's polarization due to stress in the windshield. And that's the kind of effect. If we have polarized glasses for gravity, we'll also be able to tell if there's anything funny going on in the universe, like birefringence in space-time, or any sort of mixing of the two modes, or dispersion, or any of those effects that come about if you have non-Einsteinian general relativity. So that's my hope for India. I think maybe the easier thing to understand is just localization. So currently we're in this state with the two LIGO detectors in Virgo because of the reduced sensitivity there. There's patches in the sky where if a signal pops off, the best we can tell you is it's kind of over there. And with the third detector running in India, it'll be more like we can say sort of over here, rather than. And that localization is essential if we want to actually look with astronomical telescopes and find out what's going on. Let me just skip through these things in the interest of time. This is just an advertisement for a new building being built in Caltech. The other thing I did during the pandemic was work on the civil construction design of a new experimental lab for myself and for others, not just for me. So we're building a new building next to our existing building, and this is called the Ginsberg Center for Precision Quantum Measurement. So all the labs will be filled up with people who do precision quantum measurement, myself, plus people doing neutral atom tweeters for quantum computers, optical clocks, and then molecular spectroscopy for beyond standard model physics. And in the top floors will be our entire quantum information department, K and P from GKP, and all the people working on topological insulators and other kinetic matter physics and quantum cryptography. I'll tell you some features of the building. It's 30 feet below grade. It has all of these things that I've designed in about vibration isolation, temperature stability. I mean, everybody who's ever had a lab knows what a nightmare it is to get campus facilities to control your temperature. So instead, we got all of the knobs ourselves, so we get to control the temperature on our own labs, get full access to that. There's full-on electromagnetic shielding of all the power lines, the elevators. The labs are covered in RF paint, which shields us from radiation from outside. And then we have separated slabs And I have one lab with fairly non-magnetic rebar for low magnetic field measurements. And then most interestingly, we have a shared laser lab central in the building with insulated optical fiber distribution throughout the lab. So any lab can share a clean laser with anybody else just by plugging into the wall as if it's electricity, the way it should have always been. And the labs are going to be called the Kip Thorne Labs because it's the donor was the Sherman Fairchild Foundation. So I don't know if Kip's ever worked a day in his life in the labs, but we named after him. And just some pictures of the labs and what they look like. You know, usually the students come in and touch my experiments sometimes when I'm not there. And so finally, for the first time in my life, I've gotten one lab where only I have the key. And so they'll have keys to all the other labs, but I'll have one personal one. Yeah, so that's close to the end of what I wanted to say. Just my main point is now we have these tools, not just AI, but large compute tools. And so when it comes to doing a complicated experiment like this LIGO thing, again, I don't think there's any more reason to not do the best thing that you possibly could have. I think we always tried to do the best that we could have, but the best that we can do now is real large-scale implementation of optimization. That means full finite element, full field solving of everything, soup to nuts, that you have in the experiment. And it's not that impossible to do, at least on the scale of small experiments like LIGO, I think. But you know, it's not all AI. I'm not saying to say, you know, go in the lab and do it for me, but I think there's got to be a way to use this tool in the best way. And so, you know, go to class and still learn your physics, but then go talk to your robot friends and see what to do next. And anyway, I'll close here. This is my group. We're looking for postdocs, so join me if you're interested. Thanks for your time.